All right, this is the continuation of the section 4.3 notes, so that we will be able to start section 4.4 when we come in on Thursday. So this is the problem that we had stopped at and did not get to in class. We're solving by the Gauss-Jordan elimination method. Remember, that is where we have a goal of getting the diagonal of ones with zeros above and below each one in our columns. And then we can then see if we have a unique solution, no solution, or infinitely many from that. So if you look at this set of equations right here, none of them are really any better than the others in terms of, none of them have a 1 in front. I will say this one, at least everything's divisible by 3. That's true for the second one's everything's divisible by 2. So either one of those first two equations would make a good starter row 1. So I'm just going to stick with the order that they were given to us in. So we have 3, 6, -9, and 15. That's on the other side of the equal bar. We have the second row is 2, 4, -6, and 10. And then we have -2, -3, 4, and -6. So the goal is to get a 1 in the first top leftmost corner of our augmented matrix right here. So I'm going to take row 1 and divide it by 3 essentially. So multiplying through by 1/3. So that's going to be my transformation to the next piece. So if we divide everything by 3 on the top row, we're going to get 1, 2, -3, and 5. Bring our other two rows over. So 2, 4, -6, and 10, and -2, -3, 4, and -6. Now you could have also divided row 2 by a 2 if you really wanted to. It's still not going to make it a 0. So it's possible because everything's divisible by 2, but we are just as easily going to be able to get rid of the 2 using the next step. So for row 2, when we go to do the next piece, row 2 is going to be, remember, we always use our pivot element to help us. We're going to do -2 times row 1 plus row 2, because remember, the goal is to zero out this element, and this is going to replace our row 2. So again, if you need to show your scratch work for that, -2 times a 1 plus a 2, -2 times a 2 plus a 4, because I'm using my row 1 and row 2 elements, -2 times -3 plus a -6, and -2 times 5 plus 10. Okay, so we'll talk about what that's going to equal in just a minute. For row 3, we need to get rid of the -2 and make that a 0. So we always base it off of our 1. So I'm going to do +2 times row 1 plus our row 3 elements. So notice that's going to give me 2 times 1 plus a -2, 2 times 2 plus a -3, 2 times -3 plus a 4, and 2 times 5 plus a -6. So notice each of these parts right here are row 1 elements, and these are row 3 elements. Okay, so if we look at our top directions, we're going to get equal to 0. This will also be equal to 0 because we get -4 plus 4. This will be a +6 plus a -6, so that's also going to be 0. And this is going to be -10 plus 10, so that's also going to be 0. So we're going to, row 2 is going to turn into a whole row of zeros. Okay, so let's look at row 3. We're going to get a 0. 4 plus a -3 will be a 1. -6 plus a 4 will be a -2. And 10 plus a -6 will be a 4. Okay, so I'm going to, on the next line down, I'm going to rewrite what my matrix now looks like. So I have row 1 is still 1, 2, -3, and 5. Row 2 is all zeros, which we will switch to the bottom row in just a second, but we're just writing what we got. Row 3 is 0, 1, -2, and 4. Okay. So anytime you encounter a row of zeros, that needs to move to the bottom of your augmented matrix. So we're going to swap row 2 and row 3. This little double arrow means swapping all the elements. Okay, so we're leaving row 1 as it is. Row 2 now is going to be the bottom row, so 0, 1, -2, and 4. And then the row of zeros is now the bottom row of the whole thing. Okay, so what we already know about this is going to end up being infinitely many, but Before we get the answer for that, you need to verify that you've worked every column as far as we can. So notice in column 1, we have a 1 followed by a whole bunch of zeros underneath it. In column 2, we do have a 1 in our second spot once we did the swap right here, but we don't have a 0 above and below it. We can't really do anything down here because our last 1 is actually a 0, so we can't actually use that to help us clear out the -3 and the -2 on that column, but we absolutely can get a 0 above the 1 in the middle. So we're going to just take care of altering row 1, and we're going to be doing -2 times the row 2 element, so that when we add it to row 1, we get a 0. So we're going to write what all of these would look like. So that's -2 times 0 plus 1 for the first group. And we have -2 times 1 plus a 2. -2 times the next element in row 2, which is -2, plus the element that matches in row 1, which is -3. -2 times 4 plus 5. So we get a 1, a 0. This will be +4 and a -3, so that's going to be a 1. -8 plus 3 is -3. So at this point, what I currently now have is my row 1 is now 1, 0, 1. And then on the other side of the equal sign, we have a -3. My second row did not change this time because remember, we were only adjusting row 1. And I have 0, 0, 0, and 0. So I know this is infinitely many solutions. We do know that. If they ask us for the parameterized solution, so this is a little bit different than when we were doing it on the 2 equations and 2 variables. So when it was 2 equations and 2 variables, essentially you could very easily locate that you had one variable where you had a 1 in the spot. So remember, this is the x1, this is the x2, and this is the x3 column. So notice I have singularized or solved, essentially. I have a piece where I have just an x1 and an x2 in their columns. I do not have that in x3 because this is where that 1 should be, and we have values above that whole thing. So whichever one you're not able to say, oh, I have that solved for that, we're going to let the x3, that last column, since that one didn't have the 1 where it was supposed to, that's going to be the one that equals t, okay? Then you're going to read your rows using t as so when you write this, we write 1x1 plus 0x2 plus 1x3. That's how you would normally write that back into equation form. Well, because we're letting x3 equal t, we're going to say that then x1, because there's just one of those, no x2, so we don't write it, plus 1t, so the 1 is understood to be there, equals -3. So we can now solve x1 in terms of t. So if we solve that, we would subtract the t over and we get -t minus 3. So that's how we can talk about -1. -1, x1. x2, notice it's the row 2. That's the one where we have the 1 with the zeros in that column. So that's x2, there's just one of them, minus 2t, since x3, that column is represented by t, equals 4. We solve that for x2, we get x2 equals 2t plus 4. We're just moving it over to the other side. So what that actually looks like as an ordered pair, because remember we have x1, or sorry, ordered triplet. It's always hard to say that. Normally you'd have x1, x2, x3. So we know that our x1 is now represented by -t minus 3, comma. Our x2 is 2t plus 4. And then comma, our x3 was the t. So remember, this is a way to symbolically represent the relationship between the ordered triplets based on the equations that we were given. So this is for any real number t. Now in MyMathLab, they may only ask you to write this part, what the x1 equals and what the x2 equals. This is just how I put it all together so you can see the ordered pairs. So for example, I'll do a couple just so you can see a couple ordered triplets, I should say, that work for that original system. If we let t equals 0, then we would have -0 minus 3, 2 times 0 plus 4, and 0. That would be the ordered triplet -3, 4, and 0. If you go back to each equation and you plug in -3 for x1, 4 for x2 and 0 for x3, you should equal the correct value on the right side. Another example would be, what if we let t equal 1? Then we would have negative 1 minus 3, comma, 2 times 1 plus 4, comma 1. So that would be negative 4, and that's 6 and 1. So notice we could come up with an infinite number of solutions, essentially, because it is infinitely many. You can even plug in fractions for t if you want to. But the idea is that this is a symbolic or parameterized way to discuss all possible triplets, since it's 3 variables. Okay, so that's what writing it this way does. So the biggest thing I find that students struggle with on this is just figuring out which one is the t. So you always look at if you relabel these, but they're variables, whichever columns have the 1s and 0s, those are not the t. The t is the one that you could not get completely finished. So that's the x3 is t. Then when you write your other equations again, so you're kind of just rereading this and turning it back into equations with variables, you let the t replace the x3. Okay, so it's not too bad. You just have to get used to doing it. All right, let's look at another example. So this one's a little different. We have not as many equations. We only have 2 equations, but we do have 3 variables, even though both of them don't always have all 3 variables. So I would write this one as my first row because it has a 1 in front. So this will be my second row. Just saves us that extra step of having to swap the rows. So this is 1, negative 4. We don't have the x3, so we put a 0 placeholder. Then we have 18. For my second row, we use the coefficients of that equation. So that's 2, negative 5, negative 3, and 24. We already have the desired 1 in the top corner. So we're going to just be trying to clear that out below it and make it a 0. So for row 2, we're going to do negative 2 times row 1 plus the row 2. So we're going to write our pieces here. So negative 2 times 1, negative 2 times negative 4. So notice I'm just grabbing all the row 1 values, negative 2 times 0, negative 2 times 18. Then we get our row 2 elements. So plus 2, plus the negative 5, plus the negative 3, and then plus the 24. Negative 2 plus 2 is 0. That would be an 8, because it's negative times negative, plus a negative 5, so that's going to be 3. That'll be 0, and then a negative 3, so that's going to be negative 3. And then negative 2 times 18 is negative 36. And then we will have that plus a 24, so that's going to be a negative 12. Okay, so I'm going to replace that on my next line down. That's my row 2. So I have 1, negative 4, 0, and then 18. On row 2, we have 0, 3, negative 3, and negative 12. Okay, so before we decide what the kind of situation is here, we definitely need to go ahead and work on getting a 1 in that second spot, okay? So when we divide everything in row 2, we're going to divide it by a third, or 1. We're going to multiply by 1/3, divide by 3. Sorry, it's always easy to say that backwards. So when we do that, we're going to get 0, 1, negative 1, and negative 4. So just dividing by 3. Okay. So notice I have a 1, 0 in the column 1. I have a 1 in column 2, but I need to get a 0 above that to be completely reduced. So we're going to try and clear out the 0 in row for that negative 4. We're going to make that a 0. So row 1 is going to be, we're going to do 4 times the row 2 entries plus the row 1. So that would be 4 times 0 plus 1, 4 times 1 plus negative 4, 4 times negative 1 plus 0, 4 times negative 4 plus 18. So we're going to get 1, 0, negative 4, and that one will be positive 2. So we go down to our next part. Row 2 stayed the same this time. We used it as our pivoting part. And our row 1 now is the new entries we see here. So 1, 0, negative 4, and 2. So what I want you to notice is there's not a third equation here. We only had two equations. So when this type happens, you actually do have a parameterized solution. You're just missing the row of zeros, essentially. So if you have, more variables than you actually have equations, a lot of times you're going to get these infinitely many solution sets. So again, I don't have a way to visualize very easily what is the one spot, because remember, we need that third row to have a 1 in that final spot. So you think of this as x3 again is going to be t. So x1 will be minus 4t equal to 2, because you're reading this like an equation and this is your equal sign. X2 minus a 1t equals negative 4. If we translate those by solving them for the variable, x1 will be 4t plus 2. x2 is going to be t minus 4 because you're adding the t over. So my actual ordered triplet would be symbolically 4t plus 2, t minus 4, and t. So again, that's for any real number t. So if we pick t equals 0, we could plug that in and get 2, negative 4, and 0 as that ordered triplet. Remember, this is infinitely many solutions. So you don't have the row of 0. So I wanted to show you one where you still get infinitely many zeros or solutions, but it's not as easy to see it because you don't get that row of zeros. But we have more variables than we actually have equations here. Okay. So a lot of times that will happen, or we'll get a no solution if there's not anything that solves. But those cases usually are special cases. Okay, so we're going to look at a word problem. Just how do we set up a word problem for this type of situation? So let's read what we have here. It says a chemical manufacturer wants to lease a fleet of 25 railroad tank cars with a combined carrying capacity of 406,000 gallons. Tank cars come with 3 different carrying capacities. So they have the 7,000 gallon, the 14,000 gallon, and the 28,000 gallon. How many of each type of tank car should be leased? So we're going to let our variables, because we have 3 different types of tank cars. X1 is going to be the number of tank cars that can carry 7,000 gallons. X2 can be the number of tank cars that can carry the 14,000 gallon. And X3 can be the number of tank cars that can carry 28,000 gallons. Okay. And what we know is that they only have 25 tank cars. Okay, so one equation we can come up with is that X1 plus X2 plus X3, however many we have of each type, the maximum tank cars we can have is that whole fleet, which is 25. So that should add to 25 of their tank cars. If they use all of them, they're going to add to 25. We also know that each one has a different capacity, and we know our total capacity that we can get up to, which is 406,000 gallons. So we know that if we have 7,000 gallons for the first type, plus 14,000 gallons for the second type, plus 28,000 gallons for the third type, and we know that that's a total carrying capacity of 406,000 gallons. Okay. And they didn't give us any other information. All they told us about these tank cars, is that we have 25 of them. And then they told us about how much they each can carry and the total carrying amount. They didn't tell us, they were leasing twice as many of the 14,000 as the 7,000. They didn't give us any other connections between these types of cars. So we are just dealing with 2 equations, but 3 variables. So we're going to write out our augmented matrix. Notice that every coefficient on the top one, those are all just 1, 1, 1, and then it equals 25. This is 7,000, 14,000, 28,000, and 406,000. Now I already have a 1 here, so I can go ahead and try and clear it out the column and get the 0 below it. So our row 2 is going to be negative 7,000 times the row 1 element, which is a 1, plus the row 2 elements. So we're going to have negative 7,000 times 1, negative 7,000 times 1 again, negative 7,000 times 1 again, and negative 7,000 times the 25. So that's all the way across that row. Then we add the individual row 2 items, so 7,000, 14,000, 28,000, and the 406,000. For this first one, you get a 0. For the second one, you should get 7,000. Double check on that. For the third one, we should get 21,000. And for the fourth one, when you work that out on your calculator, you'll get 231,000. Okay, so my second part of my augmented matrix now, I have 1, 1, 1, 25. And I now have 0, 7,000, 21,000, and 231,000. Okay. So now we want a 1 member in that second column in the bottom spot, because we want it to be a member diagonal to that. Or the next available essentially integer. So this is a 0. So now we want to try and see if this can be a 1. So we're going to divide row 2 by 7,000. Okay, so that's what's happening on the next line. So I have 1, 1, 1, and then 25. If you divide each of those by 7,000, we'll get a 1, a 3, and the last part is a 33. Okay. So what I currently have is I have my first column done. My second column has the 1 where it needs to be right here, so that we have our kind of, it's to the right of the previous rows. So we need to 0 out the 1 above it. So we're going to alter our row 1. Now this one is really tricky sometimes for people because they're both 1s. So you don't really need to multiply by a different number, but you do have both positives. So we're going to multiply our row 2 by a -1 just to turn this negative for a second. Then we add it to row 1 to get it to be a 0. So sometimes if you have the same sign and it matches, you just need to change the sign of the one that's our pivot. Okay, just while we're doing the arithmetic. So that's going to be -0 plus 1. We're just working out our elements. -1 plus 1, -3 plus 1, and -33 plus 25. So we're going to get 0, 0. We're then going to get a -2 and a -8. Okay. So my next part of my matrix, my augmented matrix, I have my 0, 1, 3, and 33 that didn't change. I have my top row now is these 4 elements. So, oops, that was supposed to be a 1 for the first one. Sorry, 0 plus 1 is still 1. It's 1, 0, -2, and -8. So you got to slow down, make sure you don't make arithmetic mistakes like that. It's super easy to do. But notice this is going to be another infinitely many solutions type of situation. There's not just one way that they could make this work for them. But the problem is this is an application problem. So there is a restriction on, you can't just pick any number on the number line. So we're going to first write our parameterized solution. So remember, this is x1, this is x2, and this is x3. So since we can actually see that we've solved kind of for the x1 and the x2 columns, it's the x3 that's going to represent our t. So we're going to let x3 be the parameter t. We're going to write that into these. So x1 minus 2t's. So notice that's the x3 equals -8. So that means x1 is going to be 2t minus 8. x2 plus a 3t. So we're reading this row right now. So 0x1, x2 plus 3t equals 33. We have x2 equals -3t plus 33. So I'm going to go ahead and write the ordered triplet. Remember, it always goes x1, x2, x3. So 2t minus 8, -3t plus 33, and t. Now, normally, if we were doing just a solving problem, we would not have any restrictions on what we can plug in. But because we are dealing with trucks, these are trucks, actual objects. First of all, t has to be greater than or equal to 0 because you can't have negative trucks or tank cars. But we actually have more restrictions than that. So I want to explain kind of how this works in a realistic problem. None of these can be negative because these represent how many of each type of tank cars that we're allowed to have. So you actually need to set and make sure each part, which are our 3 parts in our ordered triplet, they have to all be greater than or equal to 0. You can't have negative tank cars. So if we put this first one in, the x1 is 2t minus 8. We set that greater than or equal to 0 and solve it. That's going to be 2t, add the 8 over, divide by 2. So right now, at a minimum, even though I know this said t had to be greater than or equal to 0, because of the first part, we are actually restricted even more. I have to have at least 4 tank cars, or I would end up in the negative answer for that first part. Then we also look at the second one, the negative 3t plus 33, set that greater than or equal to 0. I would subtract the 33 over. Now, when you divide by a negative, you have to remember this was a review of the inequalities from day 1 stuff. You have to flip the direction of the inequality. So it's less than or equal to 11. So what this actually means is that we do have infinitely many solutions, but there's a restriction. This is kind of this is the symbolic form for how many tank cars can they choose, but it's restricted. We have to have the number of tank cars that we're dealing with for T. So that's that T right there, that third one. So the ones that have a capacity of, what was that? 28,000 gallons. Okay. So the number of 28,000 gallon carrying tank cars that we had, that T, because that's what we were solving for in all these, it actually has to stay between 4 and 11. Now, I know this last one says greater than or equal to 0, but this trumps that. This first one says, no, I have to be greater than or equal to 4. The one that goes to the biggest is, no, I have to be less than or equal to 11. So I need to be this last number, this group right here, the ones that are the really big trucks that they have, the tank cars that are really, really big. They cannot have more than less than 11 of those, or sorry, I'm saying that backwards. They can't have more than 11 or less than 4. They have to be in between that. Now, so that means I could plug in any integer between 4 and 11 and come up with all of the combinations. Okay, so this is a little different. This word problem is restricted to a real life situation. So you can't just say, oh, I can plug in anything I want for T, because T represents an object in the real world. Okay, so just be aware that the word problems do have restrictions because they have to be realistic to the world we live in. All right, so this is the last 2 questions that'll finish off this video. They are dealing with an application to algebra. So it's dealing with quadratic equations, kind of. So this is the equation for a quadratic equation. We're not going to have you do anything with like the quadratic formula with this right here. We're just trying to look at the situation that they gave us. So they told us, and these remember X's and Y's. Ordered pairs are just X's and Y's. So they gave us 3 points that go through our equation, but they don't tell us what A, B, and C are. We are trying to find A, B, and C. So the way that you approach this problem is we're going to turn it into a system. We're going to plug in these Y's and X's and come up with 3 different versions of this formula. And we're going to be solving for that A, B, and C. Okay, so that's they're going to be our variables, the A, B, and C. So if I plug in this first one, I'm going to say that 9. In fact, I like to write it the opposite way, so it looks more like our standard form that we're used to for systems, ax squared plus bx plus c equals y. I know that's not how we usually write it in algebra, but when we did our systems of equations and stuff, we usually had the constant over here by itself. So that would be a, now x needs to be squared for this first part. So -2 squared plus b times an x, so that's a -2. We don't know c, but we know that y, their constant in this equation here, is 9. So we work this out until we have an equation, like what we're used to seeing. So you square this, that's be 4. So 4a, it would be negative here because we're getting a -2 times b. So -2b plus a 1c equals 9. So notice that now looks like kind of x1, x2, x3. Okay, let's do the next point. So now this time we're plugging in 1 for x and -9 for y. So a times 1 squared plus b times 1 plus c, because remember a, b, and c are kind of functioning as the what we don't know. and that's going to equal -9. So just working this out a little bit more, 1 squared is just 1. So this is going to be A plus B plus C equals -9. So there's my second equation for my system. And then the third one, I'm plugging in 4 for X. So A 4 squared plus B times 4 plus C, and then my Y is 9. So this is going to be 16A 4B plus C equals 9. Okay, so this is like a system right here. We've got a system where instead of X1, X2, X3, our A, B, and C are kind of functioning as those unknown variables. We have one equation I think would be best as the first. That's this one right here because it has a 1 in front. So when I go to write this as a matrix, I'm going to put that one on top. So 1, 1, 1, -9. It doesn't matter for the other two, so I'm just going to put them in the order that I got them. So 4, -2, 1, and 9. 16, 4, 1, and 9. So we have our 1 in the top. We're going to try to clear out that whole column and make everything below it zeros. So we need to come up with our directions for that. So row 2 is going to be -4 times the row 1, which is our 1, plus the row 2. Okay, and then R3 is going to be -16 times the row 1, which is our pivot guy, our 1 up here, plus the row 3. Now we've gotten to a point where we've done a lot of these practice-wise, so I'm just going to write the answers that we get. If you feel like you need to write out all the scratch work, please do. But just for, ease of getting through the problems, I'm going to just go ahead and say I did it offline on my calculator. So I've got my top row is exactly the same, 1, 1, 1, 1, and a -9. For my second row, once I do this calculation for each group of row 1 and row 2 elements, I get 0, -6, -3, and 45. For my third row, when I do -16, all row 1 elements and then add their corresponding row 3 elements as I go, so doing all the arithmetic, I got 0, -12, -15, and 153. Okay, so you'll probably want to double check me on all of that, but that's what I got. Then we're going to look at this element right here, the middle of that next diagonal part. We need to make that a 1. So I'm going to take row 2 and multiply it by a -1/6, or you can think of dividing by -6 as we go through. So this is going to create some fractions. It doesn't all divide by 6 evenly. So we have 1, 1, 1, and a -9. For this, I get 0. That'll be a 1 where the -6 was. -3 divided by -6 is a +1/2. 45 times a -1/6 or divided by a -6 is going to reduce to -15/2. You want to leave it in fraction form. And then we didn't do anything to the bottom. So -0, -12, -15, and 153. So notice now I have my 1 in that correct position so that we can zero out everything above and below that. So if you look at this next part, row 1, we need to get rid of the 1 that's right above our circled 1. So we're going to be doing negative of our row that we have the 1 circled. So that's negative row 2, because we want to make it negative. So when we add it to that row 1, it goes to 0. Row 3, we want to do +12 times our 1, which is our row 2, and add that to our row 3. Remember, we're just focusing on what does it take to zero those elements out. Everything else gets adjusted based on the math that makes the zeros. So I did this offline as well. So I've got my row 2, remember, is coming over not adjusted at all because it was the one we were using to pivot. And then for our top row, we're going to get a 1, a 0, a 1/2, and a -3/2. That's what I got when I did the arithmetic for that one. For our bottom row, row 3, I got a 0, a 0, a -9, and a 63. Okay. So now we are done with our column 2. We have a 1 in the middle with zeros above and below it. So that's always the ideal goal. So now we're focusing on this -9 and how to make it a 1. So we're going to take row 3 and divide it by -9, or you can think of that as multiplying by -1/9, the reciprocal. So when I do that on my next line down, all my other rows are just coming over as they are currently. And my row 3 is now 0, 0, +1, and -7. Okay. All right, so we're really close. We have a 1 in the bottom corner here, but we need zeros above it. So we're going to try and adjust rows 1 and 2 using our arithmetic combinations. So for row 1, we're going to be doing a -1/2 times row 3, because that's where my pivot is right now, plus that row 1 element. So that's -1/2 plus 1/2. So that's going to zero out. Row 2 is the exact same thing. We just want to make sure we reference row 2 when we add the elements. So -1/2 times your pivot plus the row 2 elements. When you work through this, you will get the following. So we get our third row stays the same, 0, 0, 1, and then a -7. Our first row will become a 1, a 0, a 0, and a 2. Our second row becomes 0, 1, 0, and a -4. Remember, this read as A, B, and C in those equations, because remember, we didn't have like an X1, X2, X3. We were looking for those ABCs, okay? So this right here says that A is 2, B is -4, and C is -7. So when we write our quadratic equation out, if we wanted to write it as a quadratic equation, we have a 2x squared, because that's the A, a -4x, because that's the B, and a -7. That's our C. So this is the actual quadratic equation. These are the actual individual values that we got when we solved it. So just to show you that this is actually legit, let's go to Desmos real quick. That we can actually use this method if we know 3 ordered pairs on a quadratic equation, we can find the equation of that quadratic. So it's 2x squared minus a 4x and a -7. So I wanted to remind you of the 3 points they gave us. They gave us the points -2, 9, 1, -9, and 4, 9. Let's check to see that those are on our graph. So -2, let's type it in, it'll actually highlight it, -2, 9. I'll have to zoom out. See, that point is on my red graph. And then I had the ordered pair 1, -9, which is also on my graph. That's actually my vertex. But I didn't know that going into it. I just saw. And then we had, I believe, was it 4? Yeah, 4, 9 should also be on this graph. So notice you can verify all 3 of the points they gave me fall on the red equation that I just typed in. So I did find the correct A, B, and C so that my quadratic contains the 3 points they gave me. So that's kind of cool that we can use it for that. It's a nice application. So there's one more of these, and it's a little different, slightly different, because in this one, you actually can skip ahead a little bit on the process. And the reason for that is because they gave you the y-intercept. That is the nicest point anybody can ever give you when dealing with an equation. So again, they told us it's quadratic. They told us these population was 30 million in 1990, 34 million in 2000, and 37 million in 2010. So they turned that into 3 essential ordered pairs. They started measuring time at 1990, so they're calling that kind of time 0. And they said that was at 30 million. So they're using millions for the y-intercept, or for all these actual y coordinates. And then they told us 10 years later, so in 2000, they had 34 million people. And then 20 years from the original time, we had 37. So they're kind of using it as we're going forward in time. Use this to estimate the population in 2030. Okay, so let's, first of all, we need to come up with an equation, because we can't just guess and say, oh, I think it's going to be 42 by now. You know, we don't know that. We don't know what it's going to be. So if you have the y-intercept, remember our quadratic is ax squared plus bx plus c, right? That's the general formula of a quadratic equation. So if you plug in 0 and 30 for x and y, notice really quickly that that works out really nice for us, because 0 plugging in for x makes the a and the b part go away, because 0 times anything is 0. So we immediately get that c is 30. So if one of your ordered pairs in a quadratic list, when they give you 3, if one of them is 0 comma number, you already know your C. The y-intercept of any quadratic is in this standard form like this is the C. Okay. So why is that helpful? Because when I go to write my equations for the other two, so remember these are my X's and these are my Y's, I'm actually going to use 30 for C instead of using a letter that, because I know that C is 30. We already showed that with the first ordered pair. So when I write the second one, I'm going to get, I like to write it in this format, ax squared plus bx plus c equals y, just so it looks more like our systems. So I'm plugging in 34 for y on this one. And then my x is 10. So a times 10 squared plus b times 10. And I know that c is 30 because we just showed that with the first ordered pair. Okay, so when I work this out, this is 100a plus 10b, and I can subtract the 30 over, equals 4. Notice this is now just a system with 2 variables, which is a lot easier to solve. Then I'm going to get the other one. I have, again, the format is ax squared plus bx plus c equals y. This time y is 37. My x is a 20, so a times 20 squared plus b times 20 plus 30 again for c, because I already know what c is. So that's going to be 400a plus 20b, and I can subtract the 30 over to be with the 37, and that's going to give me 7. So notice I have 2 equations now. I already know c is 30, so I don't have to do anything else with that, and I just need to solve for a and b. So we're going to take just those 2 equations and put them in that augmented matrix to figure out what a and b is. Oops. Writing and talking doesn't work. So 100, 10, and 4. And then 400, 20, and 7. Okay, so remember, goal is to always have a 1 in that first top corner. And honestly, neither one of these is great because we're going to have to divide by big numbers. So I'm not going to swap any rows. I'm just going to do row 1 is 1/100th of its original self, or dividing through by 100. So that's going to give me a 1. 10 over 100 is 1/10. 4 over 100, so you got to think you're timesing 4 by this 1 over 100. 4 over 100 is 1 over 25. So I'm just reducing those as I go. Then I have my 400, my 20, and my 7. Now we want to get a 0 below this. So we're trying to use this 1 to help us zero out the element 400. So row 2 is going to be negative 400 times row 1 plus row 2. So if we want to show your work, so I'll show my work on this one a little more. So we're doing times 1 plus the 400, negative 400 times 1/10 plus the 20, negative 400 times 1 over 25 plus the 7. Okay, so this first element will be 0. This is negative 400 divided by 10 is negative 40 plus 20 is negative 20. And then we get negative 400 divided by 25. Off the top of my head, I don't remember what that is. It's been a long day, so hang on just a second. Let me get my calculator. So 400 and it's negative, and we're dividing it by 25. That is negative 16 plus the 7. I get negative 9. So remember, this is going to replace the 420 and 7. 0, negative 20, and negative 9. That's my new row 2. So we have our 1, 1/10, 1/25. Now we have 0, negative 20, and a negative 9. Our goal now is to get a 1 in that bottom right corner right there. So we're going to divide row 2 just to get this to be a 1. We're going to divide it by negative 20, or you can think about that as multiplying by the reciprocal of negative 20. Okay, so that's going to give me, nothing's changing right now on row 1. We're just trying to get a 1 in the row 2 correct column. So that's going to be a 1, and then negative 9 over negative 20. That's not reducible. You could try it on your calculator, but it's just going to be a positive because it's negative divided by a negative, essentially, or multiplied by a negative. So it's going to be just 9/20. Okay. So final step is we need a 0 above the 1 right here. We need that to be zeroed out. So row 1 is going to have to be negative 1/10 times row 2 plus row 1. So you might want to write out your work. Negative 1/10 times 0 plus 1, negative 1/10 times 1 plus 1/10, negative 1/10 times 9 over 20 plus 1 over 25. That one will probably be the one you'll need your calculator for. This first element is a 1. The second element is 0. This would be negative 9 over 200 plus 1 over 25. So get your calculator out, get a common denominator or whatever you need to do for that. But I got that it came out to negative 1 over 200, because if you get a common denominator, this is 8 over 200. So we get negative 1/200. So that's going to be, now let's write out what this looks like. So we have 0, 1, and 9/20, right? And then on the top row, we now have 1, 0, and negative 1/200. So remember, we were just solving for A and B because we already knew what C was from having that y-intercept given to us. So this, remember, is column A. This is column B. So here's my A. Here's my B. And then if I wanted to write this quadratic formula as it's supposed to be, remember, ax squared plus bx plus c. We know c is 30. We know a now is negative 1 over 200, or x squared there. B is a 9 over a 20, x, and then c was 30. So this is just plugging the a, b, and c back into this to get the equation for that quadratic. Now, there was a follow-up question on this problem. It says, use your model, so my equation that I just came up with my A, B, and C, to estimate the population in 2030. Now, you have to be careful with this. They're counting from 1990. So notice that was year 0. 2000 was 10 years in the future. 2010 was 20 years in the future. So 2030 is actually a 40-year jump from 1990. Okay, so that's how you have to look at how they're measuring their jumps. Their times all were referenced back to 1990 as year 0, essentially. So we need to plug in 40 to get that estimate. And then this is our last problem for this set of notes. Because we are going to pick up in class on Thursday with 4.4, and I will adjust the homework, of course, to match with that. So if we look at this, we need our calculator for this guy. We got 40 squared we got to do first, because remember, you always do your order of operations. So 40 squared, find my square button. Oops, I squared it twice. Hang on. Clear that out. 40 squared, and then we divide that by that negative 200, essentially, because that's the fraction, is that reciprocal of 200. So that's a negative 8 for this first term. Okay. 20 goes into 42 times. So that's going to be 9 times 2. So that's going to be 18 plus 30. So that's 10 plus 30. That means we would have approximately 40. I believe we were in million for the number of people they estimate that would be in California, living as a population of California for 2030. So they're estimating the population of California in 2030 based on the model that we came up with. So this one was a little more involved. You had, in terms of the actual final answer, you had to plug back in, and we got some nasty fractions. Sometimes the world doesn't work pretty. So just remember though, that if you have no y-intercept, so like if you have no y-intercept, you're going to have a system of 3 equations to find your A, B, and C. If you're given a y-intercept for your quadratic, plug that in first. Notice that C is equal to that y value for that y-intercept, and then you can use that in your other 2 equations so that you only have to solve for A and B. So that's just, if we didn't need to plug in into the end, we actually had a lot less, math we had to work through for this one, just because we only needed A and B. All right, I hope that helps you get through section 4.3. Make sure you have tried some of the homework before Thursday's class, just so you know if you have general questions about the process. This process is one that looks deceptively easy sometimes when you watch it enough, but you need to practice it on your own to make sure you're good. Also, make sure you read my announcement about badges, because that system is a reward system we're giving students for finishing your homework on time, at least 80% mastery. So every time a due date comes up for pretty much for each module. So we had 4 homework assignments in module 1. If you had each of those done at least 80% by the due date it was due, that earns you that badge for module 1. If you earn 2 out of 3 module badges, so for weeks 1, 2, and 3, if you earn at least 2 of those weekly badges, those module badges, then you get a second attempt at your lowest quiz over the midterm material. Same kind of rules will apply for the final. There's weeks 5, 6, and 7, so there's module badges linked to each of those. If you get at least 80% on all homework by the correct due date for each of those assignments, each module that are in each module, that earns you that module's badge. And then if you earn 2 of 3 of those, we give you 1 week that you can have a not so great week, essentially. If you earn 2 of the 3 of those, you get a second attempt at one of the quizzes that's in that second half of the class. So that's 2 different possible quizzes you could get another attempt at if you didn't do so well. So I won't be opening those second attempts until we get it'll be like that review kind of time for the midterm and the review time for the final. If you've met the requirements by that point, I will send you an email specifically saying, hey, congrats, you did what you're supposed to do for badges. You get to have a second attempt, and I will tell you which quiz I will be reopening, because I look at which one's your worst out of the 3 that you attempted for studying, for the midterm or the final, depending on which section of the class we are in. All right, hope that helps. Have a wonderful day. I'll see you guys on Thursday.